Good morning. I'm sorry. So welcome to this distinguished talk from Access Bank Center on Math and Computing. I am Professor Gopal Krishnan, convener of the center and also a professor in the aerospace department here. To tell you, many people don't know what is it. This was started in 2023 January with a goal to promote math and computing across disciplines. So it's not only engineering, it's not only science, it's biology, it is medicine. Wherever we can use Axis Bank. The primary goal is to promote through funding extra scholarships to our master students, PhD students. We had a number of postdocs. Number of visiting professors from across the world have visited here. And we also fund focused workshop in the area of maths and computing, some outreach programs. We also fund some very bright BTech interns in the areas and through our assistance with Indian Academy of Sciences. So we do everything to promote math and computing, that's the goal. And here we are to hear one of the areas in the area of medicine, neurology, where we have a very distinguished speaker in Professor Matthews. So before I introduce, I would like to welcome him with a bouquet. So this talk is organized jointly with Center for Brain Research. So I welcome Professor Hari, Director, he is here. So I'd like to welcome him with a bouquet. So Professor Hari is also a professor in our EC department. So before we start the lecture, it's my pleasure to introduce Professor Matthews. So I've known Matthews for maybe 10 years now, maybe 6-7 years. We had a lot of interaction in the area I work, in the area of structural health monitoring. So Professor Matthew is a professor in the School of Electrical Engineering and Computer Science at the Oregon State University, US. And is currently visiting as a Satish Dhawan Institute of Eminence professor in the department, and of course Professor Hari is the host. He received his PhD and MS degree in electrical and computer engineering from University of Iowa City, and his BE degree in electronics and communication engineering from REC, that is NIT Trichy. So prior to 2005, he was in the Department of Electrical and Computer Engineering at University of Utah, where he served as a chairman of the department. Chairman of the department from 1999 to 2003, and as the head of the School of Engineering and Computer Science at Oregon State from 2015 to 17. His research interests are in the area of nonlinear and adaptive signal processing and application of signal processing and machine learning techniques in neural engineering, biomedicine, and structural health management. He is one of the world-renowned expert in the area of signal processing. Matthews is a fellow of IEEE, and he served in many leadership positions in IEEE Signal Processing Society. He is a recipient of the 2008-9 Distinguished Alumni Award from the NIT Trichy, IEEE Utah Section Engineer Year of the Award in 2010, and Utah Engineer Council of Year Award in 2011. He was a distinguished lecturer of IEEE Signal Processing Society for 2013 and 14, and is the recipient of 2014 IEEE Signal Processing Society Meritorious Service Award. So we really have a very distinguished person, and so I request Professor Matthews to deliver his lecture today. It's a very interesting cross-topic, merging the medicine, neuroscience, engineering, machine learning. Anyway, I will give it to you. Professor Matthews. Thank you.
Thank you, Gopal, for that very kind introduction. And now I have to do justice to that introduction. Let's see what happens. So I'm going to talk about something I've been working on for the last 4 or 5 years on seizure detection in people with epilepsy. I call it electrographic seizure detection because everything we do is based on electrical signals that you collect, record from the brain through EEG signals. I also want to say that I use the term forecasting and prediction in about the same way. There are slight differences in how they are used in literature, but for me, there is not a difference between if I say prediction, if I say forecasting, I don't mean differently. Okay. So let me start by just acknowledging my students. This is my group. It's called Information Processing Group. We do signal processing and machine learning with applications in neural engineering, structural health monitoring, audio, and so the thing is, we will do almost anything if there is signals in it. Signals mean only that you have information available to you from some source, and as long as you have information available, we don't worry about what the application is, as long as there is some societal good to the application that we work on. And so most of the applications we have been working on in recent years have been in biomedicine. One group of activities involving paralyzed people or amputees. We look at reanimating their missing limb or paralyzed limbs. Okay. The other work that we have been doing recently is what I'm going to talk about. Let me also acknowledge NIH and Epitel because they are the ones who actually supported this work financially. Epitel is a startup company in Salt Lake City, Utah, and they have been looking at how to translate a lot of things that we know into practical systems in monitoring epileptic people. Okay? And we'll talk about that as time goes on. These are my collaborators on this particular project. The top three are my students. The first two in the bottom row are members of Epitel, and the other three are medical doctors, epileptologists, who have been leading the collection of data that we need badly to work on these things. Okay, epilepsy is a disorder that causes sudden and uncontrolled electrical activities in the brain, basically. Okay. These activities disrupt normal brain function, causes sensory disturbances, convulsions, and loss of consciousness, and can be even fatal at times. There are about 50 million people estimated to have epilepsy in the world right now. Every year, 5 million new people are actually diagnosed with epilepsy. The cost of treating epilepsy is not cheap. It's estimated to be around 120 billion US dollars a year. Even then, about 30% of the people who have epilepsy, none of the medicines work. Let me talk about the need for long-term seizure monitoring. Detecting seizures in a timely manner can provide a patient with potentially life-saving assistance. We are doing a lot of work in this area with the notion that post hoc evaluation, reviews of seizure patterns are important. Basically, you have a patient equipped with a sensor or more. We collect data. It's automatically reviewed by some machine, okay, and say, here is a seizure. It may be this kind, etc., etc. Okay. Of course, the machine will make mistakes, but even when the machine makes mistakes, our thought is that if we can actually make the amount of data that needs to be reviewed 1/10 of what it used to be, that's helping the doctors quite a bit. Okay, so that's one. And of course, knowing the seizure type is in fact required. I haven't talked about what seizure type means even here. I will talk about that later. Okay, knowing the seizure type is important for medical providers to actually prescribe medicines, come up with a proper treatment plan. Okay, and of course, if you're a patient, you would like to know if you're going to have seizure in the next 5 minutes or 30 minutes, because if I know, I can actually plan my activities in such a way that I don't do anything dangerous at the time my seizure comes. So I talked about electrographic seizure monitoring. This is just a picture I lifted from an NIH website. Okay, 18 channels of seizures, or EEG, are actually in here. What happens is, if you look here, that's where the seizure is, and you can see that the characteristics of EEG are significantly different during the seizure than at other times. Okay, so EEGs do contain information about seizures and possibly seizure types. In fact, not possibly, yes, seizure types. Okay, and so observing, monitoring the EEG signals would actually provide a very useful way of evaluating seizure occurrences and the type of seizures that came through, and so on and so forth. Okay. So what's the problem then? EEGs have been around for a long time. If you want, the standard of care is the epilepsy monitoring unit in hospitals, basically, where you would actually fit you with 19, 21, 32 sensors that can monitor all parts of the brain. Okay. The trouble is, if you want to monitor this patient for a long time, you either have to stay in the hospital, epilepsy monitoring unit, or you have to carry very large, very heavy things with you all the time. Okay, not a very enticing prospect. Okay, what if we had this one sensor? By the way, this is the sensor that they're wearing. Okay, one sensor, and one sensor may not be able to monitor all of the brain, but it can monitor about a quarter of the brain. Okay, if you know that most of the time this patient is going to have a certain type of seizure that emanates from a particular part of the brain, then you can actually place the sensor in the right location and hope to actually capture most of the information. Okay? So Epitel is a company that's trying to market this device and the algorithms associated with seizure detection and seizure prediction and so on and so forth. Okay? I've been working with them for the last 4 years, trying to actually figure out some of these things. So the idea is you would have one, yes.
Previous picture, was the person wearing two sensors behind the ear also? Or
No, this particular picture only shows one sensor.
what is the one behind his ear?
This one?
What is that?
Oh, I had never noticed it. So there are, there are two different modalities that they use. Okay, one is a single sensor, other is 4 sensors.
4 sensors.
Okay, so that you can monitor the whole brain. Okay.
But that is the ear.
Yeah, behind the ear, I think that's the location normally selected. Like, for example, look here.
That's
That's where it is. Okay, I had never noticed that before, even though I had the picture for a long time. Thank you.
That could be the reference also.
I don't think it is. In this particular case, I think he was wearing multiple sensors. So, anyway, the notion is get the data, send it to the cloud, do the work there, send it back to either the caregiver epileptologist or whoever it needs to go to. Okay, and the idea is that you can actually wear this thing throughout being, when you're doing something, even if you're taking a bath, if you're working, if you're going someplace, if you're driving a car, it doesn't matter what you're doing, you can wear this thing. Okay, and it will not be an inconvenient addition to your body. Basically, that's really it. Okay. Okay. So let me talk about our goals. We want to successfully detect all types of seizures. Again, types. I know I haven't explained what types mean. Okay. With high sensitivity and for small number of false alerts. Okay. But we want to do that using only EEG data from a single wireless wearable sensor. That's the key. Okay. There's a lot of work that has been done in multi-channel algorithms. Okay, but one channel is not that easy. Okay. Oh, and then the second part of this thing is, if possible, I would like to not just know that a seizure has occurred. I want to know what kind of seizure has occurred. Next slide is important. The other thing that we want to do is to make sure that we don't want to train on individual patients. We don't want to make this personal. We want a generalized algorithm. Okay, so that I want to train it on a certain number of people, and then I want to be able to use it on other people. Okay, that's really what we're trying to do. Okay, I've been talking about seizure types for a long time, so let me just explain what kind of seizure types I'm dealing with. Okay, in the classification of seizure, the types are determined by where the source is. This part of it is. Okay. For example, we will talk about focal seizures quite a bit in this talk. Okay. Focal seizures are initiated in some localized part of the brain and stays there. Okay. You can have focal initialization as focal, and then it can actually spread all over the brain. That could happen, but if we talk about focal seizures, it means that it stayed in the location where it was initialized. Okay. And then there is generalized onset. It's coming from everywhere. Okay. In focal seizures, the kind of seizure that I am most interested in is what's known as seizure with impaired awareness. So you kind of lose consciousness a little bit. Okay. Yeah, among generalized seizures, there are two types that we will talk about. One is tonic-clonic, which actually you become stiff, you have jerky movements, you lose consciousness, and a whole bunch of things. It's very obvious what is happening there. You will see people going through convulsions. Okay. There is generalized absence seizures, where you might not even often know that it happened. Often you might see the person just staring at you because they lost consciousness for a little while, just for a few seconds, and stare at you, and that's it. Okay. So the three kinds of seizures that we have worked with most are focal seizures with impaired awareness, generalized absence seizures, typical absence seizures, and then tonic-clonic seizures that comes with stiffness of the joints and jerkiness and all those things. Okay, our goals are not over. The holy grail in this particular problem. Try to predict seizures in advance. That's not an easy problem to solve. Okay? But we are making an attempt. So this seizure prediction problem, what we're doing is we are making it personalized. Yes?
Question, sir. So, depending on the type, is the placement of sensor also required, the specific placement depending on the type of seizure?
Not necessarily the type. It depends on where the seizure is initiated. If I have a sensor here, and the seizure was initiated here, I may not actually capture it. Okay? But in a lot of situations, my understanding is, there are neurologists here, they will know probably better than me. My understanding is that a patient will get similar type of seizures, similar initiation, similar locations where the seizures are initiated. Okay, if that's the case, if we know, then the location is okay. Otherwise, the understanding is that we will miss some. Okay. Okay, and as I said, the yes.
One small question. Can a person's seizure type change with time?
You can have multiple types of seizures. Yes, two different things I will tell you. You can have a focal seizure that was initialized at some location, and it can actually spread out into something, and it can become tonic-clonic. Okay, the same seizure can evolve into something else. Okay, I have not heard of absence seizures where you stare at each other a little bit. Absence seizures evolving into something else. I've read about focal seizures evolving into something else. I have data that does that too.
But a generalized seizure shall not morph into a focal seizure, is it?
Say it one more
A
time.
generalized seizure will not change into a focal seizure, is it, over time?
I don't think so. I have not heard about that. I don't have data like that. Okay. Thank you. Okay. So, what do we have to do to detect a seizure? Right now, I'm going to talk about detection of seizures in general, and then we'll talk about. Okay, let me just take a step back. The three types of seizures I talked about, they have very different signatures, characteristics. Okay, and it's easier to actually, if you know that you are looking for a type of seizure, it's easier to design an algorithm that will actually detect that particular type of seizure rather than trying to design an algorithm that would actually detect every kind of seizure, because the characteristics are so different that you may not be able to do that. Okay, so what we have ended up doing is start with seizure detection for specific types of seizures. So we'll build three different types of seizures, for example, seizure detection algorithms, for example. Okay, and then we are trying to figure out ways to actually combine them, okay, so that you can do a general seizure detection. Okay, so what do? You capture the data from the sensors. We do some pre-processing to enhance the data, clean up noise and other kind of things that you don't want, information you don't want. Then you extract the features. When you train the algorithm, when you actually design your algorithms, you take the extracted features and figure out which ones are really important. And that's what we mean by feature selection. Okay, and then we do the decision, we divide the data into segments, small segments, okay, typically 2 seconds long segments, and we actually make a determination as to whether the seizure, whether that segment is part of a seizure or not. Okay, and then do some post-processing by which we can actually convert the segment level determinations into event level determination. We need that in the end. Okay, and then we'll talk about characterizing the performance of those things. Okay, so what I will do is I will spend one slide each on each of these boxes, okay, so that we go through the steps quickly, and then we'll talk about enhancements to the basic algorithm we can do. Okay, I think you'll find that this talk is more broad and not very deep. If you have more questions, just ask. I may be able to help you. Otherwise, I'll tell you, go talk to my student. Okay? Because it's all done by my students. All right. Pre-processing. We start with a 60 hertz notch filter, and then we have a band pass filter, typically 1 hertz to 40 hertz pass band. Okay? You might ask me, why do you need a 60 hertz notch filter? The band pass filter doesn't usually take out all of the 60 hertz signal. Then we do a data standardization. Basically, different sensors might actually have different noise characteristics. Okay, so one of the things that we do is we normalize the data. We call it standardization. That's because of preferences of certain group of people in our field, in this particular field. Okay, we normalize the data with an estimate of the noise level, noise variance, basically. Okay, and that we do by basically looking at the signals for a long time, maybe a couple of hours in the past, and looking at where the variance was the smallest, and we just say that the smallest variance in that area is a good estimate of your noise variance. Okay. Okay, I explained that already. Okay. So that's the pre-processing we do. So everything is fairly straightforward and simple approaches to doing these things. Feature extraction, I will tell you what kind of features we have been using. Okay, we talked about 2-second segments already. What we have found is frequency domain characteristics are fairly important in seizure detection, at least the way we have been doing. That has helped tremendously. Okay. Root means square, sorry. Yeah, that's my mistake. I should have been. Okay, anyway, thanks for asking. So the signal strength in the delta, theta, alpha, beta bands, we have found it to be important. Okay. Delta band is 1 to 4 hertz after the bandpass filtering. Theta is 4 to 8. Alpha is 8 to 12, and beta is 12 to 30 approximately. Okay. We have found that the strength of the signals in these bands are indicative of, or relative strength, let me put it that way, are indicative of seizure occurrence many times. Time domain characteristics, in particular statistics like skew and kurtosis, we have found to be particularly useful. Complexity domain, basically variations of different entropy measures. Okay. One of the things that you will find is that the initial selection of the features, we don't care if they are overlapped, if each of them can be estimated from the other features and so on and so forth. We'll figure it out later and actually throw out all the overlapped features. Okay. Okay, so this is just the set of features we're initially considering. We started with something like 23. There are people who have looked at 60, 70 different features also, but we have been sticking with our 23. Okay. So, as I said, we look for features that are highly correlated with each other, and then basically say we will only use one of them because they tend to have the same information more or less. Okay. So you retained one of the many features that are correlated, highly correlated, and now you have features. You are left with features that are not dependent on each other in some sense, or correlated with each other. Okay. So then what do you do? Out of this remaining set, we select what is most indicative of a predictive of the labels. Labels being our knowledge about whether the segment was a seizure related segment or otherwise. Okay. Ideally, the easiest thing to do, the right thing to do is to actually look at mutual information of the set of features with the labels. Okay. Find the features that gives you the most mutual information, and that's probably the easiest thing to do from a theoretical perspective, but typically it's not computationally easy to do high dimensional mutual information calculations. Okay. So we have been looking at approximations and suboptimal methods to do that. Okay. And There are plenty of suboptimal methods available in the literature. There are plenty of suboptimal methods available in the AI packages or machine learning packages that you can get. Okay, so use any of them. That's probably okay. Okay, training the machine. So we basically label the segments as a 1 if it even partially overlaps a known seizure. Again, remember, like, you're looking at designing the algorithm right now. So you're training the algorithm. You have information about the seizures because people have looked at the data and determined that seizures happened here and seizures did not happen there. Okay, and even if there is partial overlap, you claim that that's a seizure event, seizure segment. Okay. Thing that you have to remember is that seizures occur sparingly. If we have 100 hours of recorded EMG data, we'll be lucky if we have 30 minutes of seizures. Okay? And we have about 40,000 hours of data available to us now. And even then, we complain about not having enough data, to be honest with you. Okay? So seizure detection is a highly imbalanced problem. If you design an algorithm that does not take care of the imbalance, you will actually get a classifier that is biased towards the majority class, basically. So you have to be careful. Yes.
What is the minimum time a seizure can occur? What is the maximum?
So I can only tell you what we do. Okay. So we don't consider an event a seizure if it's less than 8 to 10 seconds.
Oh, 8 to 10 seconds.
Yeah.
So 4 segments.
Yeah, 4 segments, 4 or 5 segments is what we
Sustained.
consider. Sustained, yeah. Consecutive segments. Okay. Now, if you have seizure for more than 5 minutes,
5 minutes.
if you have, that's supposed to be very dangerous, right? There's a terminology for that. I can't remember what the terminology is. So a lot of times, pardon me?
Status.
Yeah. Okay. Status epilepticus, right? Yeah, right. I'm learning from the doctors here. So, anyway, so oftentimes we tell ourselves that if I think we have a few cases where the seizure actually extended for more than 5 minutes. Okay, but we don't normally look at that long seizures in our work. But again, it can be long, but it's not always. It's very rarely. Okay. Yeah.
When you say overlap, because these are waveforms,
Yeah.
I would guess that you are looking at overlap in some sense of similarity measure, right?
So no. Here overlap is totally different. What we're saying is some epileptologists have looked at the data and marked the data to where the seizures are, starting point and ending point of every seizure, right? So now that information is available when you design the algorithms, right? So you look at the 2-second seizure segment, 2-second segment, and basically say, is that segment going to fall, any part of that segment going to fall between the starting and ending point of a seizure?
So that's basically the signature, so to speak.
Yeah, it's the waveform. If the waveform is part of the seizure duration, we say that there is overlap, and therefore that whole segment is marked as seizure. Make sense? Okay. Yeah.
Is there any pattern among the 4 waves, frequency domains of delta, theta, alpha, beta, then occurring like alpha after beta? Is there any pattern?
So
That also changed.
yeah. Okay. I have to go back and look at, because I worry about, delta is the lowest, yeah. So I can never remember which one comes first, you know. So if you're looking at delta, that's a low frequency signal, right? So that'll be smoother than the beta bands, because it has signals in the 12 to 30 hertz band. That's one thing you can look for. But that's standard because that's a standard issue basically. Okay. Is the pattern going to change from no seizure? Actually, the terminology people use is non-ictal. Okay. Is the pattern going to change from non-ictal data to ictal data? Yes, that's what we're looking for, right? How does it change for delta band versus beta band? I don't necessarily know the answer right now, but they do change. Okay, and that's really why we are including those as features. Okay, good enough. Okay. Okay. Okay, we finished this thing if my memory is right. Okay. Okay. Now you have made a determination for each segment as belonging to seizure or not seizure, right? So now you have to, if we only know information about the segments, it's not really helping us much. We need to actually stitch together that information to decide where the seizure occurred, the actual event occurred. Okay, and that event is going to happen over multiple segments. Okay, we need to identify a contiguous set of segments that we claim to be seizure, and or the rest of it we claim to be non-seizure, right? So how do we do that? So the thing is, we do morphological post-processing, but I'm going to explain it in fairly simple terms. Okay? Essentially, there will be isolated ones and zeros in the determinations. Okay? For example, if you look at the zeros and ones, basically it's saying that there was the first 8 or 9 segments were determined as zeros. That means no seizure. Then there was a 1, then 4 more were zeros, right? So the 1 is an isolated event. And we don't believe that there was a seizure just for that 2 seconds. Okay? You get that, you just make the 1 0. Okay? So basically, we have to determine how long the minimum length of a seizure is going to be, or minimum length of an event is going to be, whether it's seizure or non-seizure events. And we have, in general, used 5 segments as the minimum. Okay? So anytime you have isolated events that are less than 4 segments or less long, we change the decisions basically. Okay? We change the zeros to 1 or 1 to zeros. Okay? So in this particular case, if you look at this, after making all the changes, there is just 1 long seizure out there. Okay? And then we'll say that here is where the seizure started, here is where it ended, this is it. Okay? That's what we do. Yes.
So the annotation would have been quite a tedious work because we look at
Right. Absolutely.
it's a most
Yeah. So that's what I was saying, like in the sense, if we have the annotations done for a training set, can my machine do the rest of it? Okay. We will make mistakes, but given that the mistakes will be made, still, if I have to only look at 1/3 of the data or 1/10 of the data, I'm better off. And that's part of the goals here. Okay. In fact, the first money-making system that this company has actually created is actually for those kind of things. Annotations, yeah. At least that's my understanding.
I have a question.
Yeah.
You said that 5-minute seizure is a fatal one.
I didn't say fatal, but it's
Nearly fatal or whatever.
can be bad, yeah.
And what is the maximum seizure time you have actually seen?
I have data that, if my memory is right, I have only 3 or 4 cases above 5 minutes. And I believe that I had one with around 10 minutes of seizure activity.
No, I'm seeing that if you look at the frequency domain characterization in the four bands,
Uh-huh.
uh, suppose you have somebody with 1 minute, 5 minutes, 3 minutes. Are these bands similar in the frequency strength of the signal? And is it not proper? Do you normalize it with for a person that with a healthy person's signature?
So we have not normalized it. Well, obviously, when we train, we have used non-epileptic patients' data as well as epileptic patients' data. So there is some normalization, standardization going on in that way. We have not gone in and explicitly done that work, but it happens as part of the training process. And the other question you asked about whether the signal characteristic change with length, it shouldn't, just the length shouldn't change the spectrum. If you're looking at the spectrum of a 2 second data, 2 second long data, I don't think it will, but I don't know if the characteristics, but it's also possible that the actual seizure characteristics are different for longer seizures over shorter seizures. So, okay. Yeah, my knowledge of the physiology is not that good when it comes to this kind of questions, but all I'm doing is explaining in the context of the data I have seen.
Is there any correlation between the run lengths, the duration, and the types of seizures?
So the absent seizures are typically short, very short, typically a few seconds to another few seconds. That's typical. Focal seizures and tonic-clonic seizures tend to be a little longer than that. Typically, I think. Again, feel free to correct me if you need to. Okay, so that's the kind of data I have seen. Let me put it that way. Okay. All right. So what we have done is we have actually gone through all the steps of creating a machine. Okay. Now, the next question is, how do you improve upon the basic machine? Okay. And I'm going to talk about one improvement before I show you any results. Okay. Just to get a sense of what we can do. So what we're going to do is we are going to talk about a two-stage classifier. So the idea is the following. Think about the seizure detection problem as an anomaly detection problem. Okay? It is an anomaly from the normal operation of the brain, right? So think about it that way. The thing is, there are many different kind of anomalies that you have that may have nothing to do with epilepsy. Okay? For example, if you're chewing, the data actually get picked up by the EEG sensor. Okay? And that might look different from normal. And the initial decision might be that I have an anomaly, I have a seizure. Okay? But that's not necessarily the case. Okay? So what we have done is we have not tried to just figure out all these problems, solutions to all these problems in a simple one-stage machine. What we're doing is we are looking at the decisions made by the machine, one-stage machine, and then when the decision is that there is a seizure that has happened, we basically look one more time. We design another device that would actually figure out from among the seizure candidates which one is the real seizure and which one is not. So what it does is it will reduce the false alarms quite a bit. Okay, that's what we do. So how does it work? So don't worry about the three different colors. Okay, they just use three different machine learning models. Basically, everything is one of them is random forest, other is balanced bagging, the third one is gradient boosting. I think. Okay, so doesn't matter too much. But the thing is, the first set of figures, first set of bars, is the false alert rate, number of false alarms per hour, when the sensitivity was 80%. Okay, so we designed the system in such a way that the sensitivity is always 80%. Okay, and then found out what the false alarm rate was. Okay, so you can see that when you have a second stage, you go from 6 or so false alarms per hour to 3 or so false alarms per hour. Okay, you can do better than that, but the second stage really helps us in this particular case. Okay, we tried a whole bunch of different variations. Nothing worked significantly better than having that second stage. Okay, if you didn't have the second stage and I tried the other variations, I will get better results, but not as good as with the second stage alone. Okay, that's what we have found. Okay, now the question is, how do you, yeah,
What is your target? What should be the false alarms per hour?
0, right? I would love 0, but no. I think it has to be sub 1 per hour.
Sub 1 per.
Yeah, that's, and if it's sub 1 per hour, it'll be even better. Okay, with there are people who claim a lot of very good results, but oftentimes they are in the segment level analysis, not in the event level analysis. Okay, but ideally, I would like to have 0.2 rather than 2, and we are at 1. With everything that we have done at Oregon State, we have come down to about 1 or something like that. When I look at this particular problem, I look at speech recognition problems about in the 90s. Okay, when I first looked at speech recognition problem at that time, we were getting 50% accuracy. People won't even believe that there was a time when 50% accuracy was considered good, right? Yeah, my expectation is that working on these things, other refinements are possible, and we'll bring it down to that sub 1 case reasonably quickly. Yes.
One more question.
Yes, of course.
So in the two-stage algorithm, if you, is your first stage, is your first stage biased more towards detecting? It's okay to get false alarms in the first stage,
Yeah.
right? You want to bias your hypothesis testing so that you minimize misses. You almost never want to miss. It's better to get a false alarm
Right.
than miss something, and then you refine it to reduce a false alarm rate.
Right.
That's the design philosophy.
That's one way of looking at it. Yeah. Okay. It's 11 o'clock. Gopal, how long can I go? I mean, 12 o'clock, yeah.
Well, maybe another half an hour.
Oh, okay. Then ask away all the questions.
I have a question.
Yes.
So I'm trying to understand the kind of data you're using here. So basically, you are using the data of an individual if they have at least one episode of the event in the data. Is it like that?
No, not necessarily. We have data from about 500 people. Not everybody had a seizure. Everybody was expected to be epileptic, but you stay in the EMU for 4 days, 5 days, and if you didn't get a seizure, there's nothing you can do about it.
So the numbers that you have shown previously are from that kind of a data where there's a case where they might not have even one seizure also.
Absolutely. Yeah. And we might actually say that there was a seizure too. Absolutely. Okay. Yes.
Continue that, it is basically classifying the features what we are extracting.
Yeah.
Right?
Yeah. That's all there is.
Yes. Good.
Okay. So the next question is, how do you identify seizure types? Well, the easiest thing to say is just design a single multi-class algorithm. Okay. But the problem with that is we may actually run out of data. In spite of the fact that I said I have 500 people's data and each of them about 100 hours each, the data is not enough for a lot of problems. So we are working with the simplest algorithms we can use, because simplest algorithms that do not require a lot of data. Okay. So the other option is to design an ensemble of classifiers performing similar tasks. Okay. And then combine the individual results to extract all necessary information. Again, this is not different from what multi-class algorithms that people do, like one for all, or one versus all versus, and things like that, right? So, for example, if you had 3 different classes that you want to actually identify, and classes plus no seizure, there are 4 classes basically. So you could either build a 4-class device system, or you can have multiple smaller systems. For example, if you want to determine between class A or class B and C and no seizure, that could be one, and build a whole bunch of things like that. Okay, and then this Venn diagram shows you different probabilities and how they are all related and things like that. Okay, using the question asked to each of these classifiers, we can actually write down the equations, and we'll be able to write for any number of seizure types. We'll be able to write. We'll be able to design enough number of classifiers that will actually give you all the information you need. Okay. In this particular case, for 3, 7 is the minimum number needed. Okay. In our case. Okay. And then it's a question of if you want to find the probability of A being the seizure, look at A, D, G, and D basically, and so forth, right? So you can actually, if you want to find A, B, or C, if you want to find a seizure, you can still this is basically looking for just seizure, regardless of the type of seizure, right? You can do that. But it turns out that, at least our experience is that, if you want to determine if seizures have occurred or not, even then, going through this process of identifying all the seizures type gives you better results. I'll show you that in a second. Okay, I said it already. Approach can be extended to any number of seizure classes. Okay. One additional thing. If you want to determine if a seizure has occurred using this kind of ensemble of systems, okay, one thing you can do is you can recognize that depending on the type of seizure, your decision thresholds can be different. You can design decision thresholds based on your estimate of what kind of seizure it's going to be. And that helps tremendously in our case. Okay? And I think I said everything I need to say. So basically, you look at the decisions made over the past several hours and use the threshold you would use for the majority case, or whatever seizures occurred most. Okay? Things like that. Okay. So let me show you some performance metrics. This basically curve is sensitivity versus false alarm rate. Okay? And for the 3 events, 3 kinds of seizures: focal with impaired awareness, generalized, absence, and tonic-clonic. Okay. Tonic-clonic is easy to identify because it's jerky conversions and all those things make it easy to recognize. Okay. Absence is focal is the most difficult ones to identify, and oftentimes the reason being there are many different types of focal seizures that happen. Everything is classified into one. Okay. And so if you actually think of this curve, this graph as a receiver operating curve. Okay. If you find the area under the curve, you would expect focal to be the smallest, absent to be next, and tonic-clonic to be the largest. Okay. And I also show you for overall AUC for determining if a seizure has occurred. Okay, that turned out to be the second largest in this case. Yes.
So this is based on all the 23 features what we were looking
Yeah.
at.
Yeah.
So okay. So
Yeah.
you would be using all the time domain, frequency domain, as well as the non-linear
Yeah.
measures.
Right.
Okay.
So this particular curve shows you the sensitivity versus FAR, false alarm rate, for the case when I was trying to just determine if I had a seizure or not. And I'm comparing a direct algorithm to an algorithm that identify the seizure types in the middle and in between, and then made the decision. Okay. And the blue is the one that actually is the multi-class case, or the one that went through the type selection, type determination. Okay. So the curves might look close to each other. They're not that close. I'll just give you an example. Two examples. 81 was the sensitivity for both cases, both algorithms. The false alarm rate came down from 3.6 to 2.5 when you actually went through the decision typing approaches. Okay? Similarly, 75 sensitivity came down from 2.6 to 2. Okay? If the sensitivity comes down, then the differences become smaller, but when the sensitivity goes up, the differences are much larger. Okay?
Do you have any space-time differential equation to model this?
Differential equations to model
This whole activity of the brain,
you,
it can lead
yeah,
to.
yeah. There are models of EEG generation. In fact, Karthik is Gopal's son. Karthik has been looking at those kind of things, but we haven't gotten anywhere with that yet.
No, it is actually because you have classifiers, different classifiers. For each of the classifiers, you have n number of data.
Yes.
Using that data, assuming certain form, we can really construct the physics-guided model.
Yeah, absolutely. We'll get there in a second. Okay. Yeah, but we haven't done the physics-guided or physiology-guided algorithms yet. But technically, yes, basically building models. There are people who have spent their lifetime building models of EEGs. So, yeah, we'll get there in a second. Oh, but I don't have enough data. All right. So we are trying to address this issue. I present it in a slightly different way, but it's not particularly different from what you're suggesting. Okay. So we want to augment the training data using synthetic data. Okay. So there are two options available to us. One is you can do feature level data augmentation. If you look at SMOT, if you're a machine learning person, if you look at SMOT, synthetic minority oversampling technique. Okay. That's what they do. Basically, you have some data available, unbalanced, high level of imbalance, okay, and you take the minority class and then interpolate between the features, okay. and then add some noise and so on and so forth, and that's what we do. Okay, so you can do feature level data augmentation, or you can do EEG level data augmentation. That's what, in some sense, you are suggesting that. Okay, and we are using something called Wasserstein generative adversarial network to do that. Okay, so we haven't gone to the physical modeling yet, physiological modeling yet. Okay. So what we have found is that EEG level data augmentation somehow helps us more than just than feature level data augmentation. I don't have a great sense of why yet, but we're still working on those kind of things. So just to give you an idea, what I have here are 3 bar charts or 3 box plots, each corresponding to the area under the curve for 3 different types of ROC curves, receiver operating curves. Okay, so the first one, this one, is the sensitivity versus false alarm rate at the segment level. Okay, the 3 colors, one is without any modification, the green is with SMOT, feature level augmentation, and the brown is data level augmentation. Okay, and you go from something like 0.83 to 0.95 or something like that, the rate. So you get significant improvement in performance by doing this data augmentation. The second set of results are for event level decisions, sensitivity versus false alarm rate. The third one is actually sensitivity versus not false alarm rate, but how long were you in the false alarm mode? Okay, because sometimes you can have one false alarm that's only 1 minute long, and another false alarm can be 10 minutes long, right? So we just looked at the time, okay, just to get a sense of what that does. In each case, you will see the same type of improvements from the basic algorithm without any modification to feature level modification to data level augmentation. Okay, but it doesn't happen you cannot just do it and get infinite number of infinite increase in the data. Okay, after about 15, if the data size up to about 15 times what the original size was, it improves. After that, it comes down. In our example, what we have done. Okay. Okay. I am going to skip this one because we're getting past our time, I think. So you can do post-processing better than what we have done. I will just... Oh, by the way, there is one thing. This is something I came here about 6 years ago. And Chandramurthy in EC actually taught me how to do Bayesian learning with pattern-coupled sparse Bayesian learning algorithms. Okay, so thanks to him, I have a different way of doing things now, and actually it works so much better. This is a box plot of the FAR. This is a box plot of the FAR false alarm rate for the original algorithm I explained. This is the FAR value for the Bayesian learning based algorithm. Okay, the median error came down from about 3 to 1 in this particular case. Okay, so the notion here is the following: seizure is a sparse event. When seizure occurs, multiple segments, continuous segments, will have seizure characteristics. Okay? So it's not only a sparse event, but it's also a clustered event, clustered sparse event. Okay? So can you make use of both of those facts to improve the probability calculations? Okay? Turns out you can. Okay? All you have to do is design a Bayesian algorithm with a prior that makes use of sparsity and clustered nature of the sparsity. Okay? And that's what we did. Okay. I said I wouldn't do it, but I just did it. Oops. Okay. Last thing. Seizure prediction. I have two slides basically. So again, quick idea. I'll just give you the idea, show you some results, and then stop the talk. So the idea is this. Between non-ictal, when there is no seizure versus when there is seizure, there is a fair amount of difference between the data characteristics. The features will show differences, and that's what we are making use of in detecting seizures, right? It turns out that a little earlier than when the seizure occurs, the signal characteristic starts changing. Okay? And it turns out even more that that change stops after a while, and then there is a period of time when the signal characteristics is even a little more different than for the pre-ictal area, this area. Okay? So if that's the case, can we design an algorithm that looks for the difference between non-ictal, no seizure, and pre-ictal, and basically say that when the pre-ictal area is done, you probably will get seizure soon after that. Okay? Turns out that there is scope, there is hope for this to actually work well.
What is the timeline that we can get segments?
The timeline is dependent on the patient. Okay, so this is an algorithm that this is an approach we can use only in an individualized manner. Okay, this is the same data that I showed you earlier in the beginning of the talk. Okay, if you look at it, you can definitely see the difference here versus difference here. Okay, you can see some differences here. You can see some differences here. Okay, so again, this is not proof, of course. For engineers, this is one example or two examples will make a proof, right? So anyway, but the thing is, we are trying to figure out if we can identify this part from here. That's in some sense one way of looking at it. Okay. Let me show you what we have been able to do. As I said, I have a bullet that will actually show that, but this is individually. You have to design the algorithm individually for each patient. Okay. So in this particular case, this length could be different from one patient to the next patient. This length could be different from one patient to the next person. Okay. And so you have to actually figure out all those things from data that you collect from the data. So even though we had 500 plus pupils data, we only had much smaller number of data where you had multiple seizures in the same person. Okay, so the results I showed you, 11 patients, 18 devices, and 37 seizures. Okay, that's what we had to work with, because we needed patients with multiple seizures in there so that we can train the machines on the earlier data and then also test it on their own data. Okay. Yeah, and as I said, this is a personalized algorithm. Alarm and predicted durations may vary with people, etc., and so on and so forth. Okay, so I'm going to stop now. What I believe I've shown you is that there is feasibility of long-term seizure monitoring using wearable single-channel EEG sensors. I think we have shown that it's doable. There is a lot more experimental validation that needs to be done, but I think it can be done. Basic signal processing and machine learning enhancement, improve performance, and I think I showed you that. Examples included multi-stage classifiers, ensembles of classifiers, dynamic thresholding, pattern-coupled sparse Bayesian learning, synthetic data augmentation, a whole bunch of different things. These are individually, they are nothing for a single processing person. These are not new concepts. Okay, but the improvements you get, enhancements you get in the application we are interested in is good. Additional refinements are still needed. For example, artifact removal. I didn't talk about artifact removal at all, and chewing or jumping or eye blinking, a whole bunch of different activities can create erroneous, incorporate erroneous data into the data we are analyzing. We need to make sure that these artifacts are actually treated appropriately. Okay, and what I said earlier, we are just in the infancy of seizure prediction forecasting technology, but I think the initial results are quite encouraging, and this is where I stop.
So you said that the pre-ictal and the alarm durations are different. You said that the pre-ictal and the alarm durations are different for different individuals. But what about the same individual? Are they same for
So
different seizures that they have?
our belief is that there will be similarities. Okay, because if this has to work, even as much as I showed you it worked, okay, that pattern had to continue. Okay.
The features are also more or less.
Pardon me?
The features are also more or less the same for the pre-ictal elements, not just the durations, but the features of the.
That's the expectation, yes. Yes.
The warning time you had shown in the table, the warning time.
Not here. Here.
No, the table.
Oh, okay. Yeah. So the idea is, in this particular case, I didn't explain that. So I showed you what the, yeah, I have to explain it. I'm sorry I didn't explain it earlier. Thanks for asking. Okay. So how do you characterize seizure forecasting, okay, or prediction? One is to say that every time there was a seizure, I predicted it, so person could actually live safely. Okay. But the thing is, I also need to know how much time the person had to worry about an incoming seizure without having a seizure. Okay. So what we're saying is that 29.5% of the time, this person was actually living in the fear that, not this person, this is on average, living with the notion that there was going to be some seizure happening soon. So 70% of the time you could live without worry, hopefully, okay? But that's a relatively large number still. Okay? 68% sensitivity is still smaller than I would like it to be too. Okay? But this is where we are.
So what is the average duration of each of the subjects which you had considered?
So my student looked at anywhere from 2 minutes ahead of time to about an hour ahead of time. And basically what she did was, she said, I don't care what you tell me, I'm going to trust you. Okay? If the system, the analysis tells me that I need to wait, I can get the data 1 hour in advance, that's what's right. And if analysis says it's only 2 minutes in advance, that's what I will do.
What is that from your experience of these results and like
I didn't hear you. Can you explain?
from your experience of these results, what is the best, prior time what you would have achieved? Like you're telling 2 minutes to 1 hour before, right? Like,
Oh, see, the thing is, there are 18 devices here, 11 patients. All 11 patients had different numbers. So I don't really know. I haven't looked at that particular question carefully enough to say.
okay. Yeah, I'm just curious that what is the best time you could achieve for any particular person, whatever you have seen around 11 patients.
Oh! I think you asked me. I answered the wrong question. I think you're asking me what's the best results I've gotten.
Yeah, out of these 11 patients.
100% accuracy, sensitivity we have gotten with many patients. Okay, I don't remember what the smallest time in waiting has been. That I don't remember.
In the previous slide, so that means you need multiple annotations like pre-ictal, then the ictal.
So
No. The morphology pattern changes.
No.
Ictal
Yeah,
morphology, post-ictal.
Yeah.
So that means you had all these separate annotations for.
No. That's not how we did it.
Okay.
We basically had an epileptologist annotate for seizure and non-seizure. Okay? And then we basically said, this is where the seizure started. I'm going to find out whether my warning period is 2 minutes or 5 minutes or 10 minutes or 15 minutes or 1 hour. So my student did the analysis for every case separately during the training process. Okay? And picked the best one. Does it make sense?
No, because when we look at a EEG in a long-term monitoring, so definitely when this ictal phase is coming, pre-ictal changes are there.
Yeah.
So now if you have a classifier which can pick up those changes, that's the pre-ictal stage.
Right.
Then that makes a very good value.
Yeah.
Suppose obviously at that level is too late for a person to do anything because already the pre-ictal changes have started. Okay. Unless until we have this vagal nerve stimulator which can instantly send this kind of a feedback. So that's one of the things that can be best achievable where it can auto, because otherwise impossible. Even if I know that I'm just going to get the seizure might come unless until drugs will not work. Only electrically you have to So I mean, this is one of the things that which the newer technologies which are hoping to solve this problem.
Right. Yeah.
The morphology is very different. The pre-ictal, the ictal and the post-ictal.
Right. So I think you kind of validated some of the things I said, but the difference between what you are proposing versus what I have done.
That's different.
Yeah. Okay. The thing is, if I can get somebody to annotate for everything, life would be really good, but I don't think so.
There's this device called RNS, responsive nerve stimulation, where it's put inside the brain. It detects the seizure in the pre-ictal state and then it sends a burst of waves, so the seizure is stopped even before it happens.
Yes.
But based on my reading and the patients that we have, it was never 2 minutes or an hour before. It's a couple of seconds. Milliseconds.
I know that, and we are trying to do a little bit differently. Yeah. The thing is, for what you are doing, if you can reliably get 2 seconds before, that's plenty enough.
It's enough for the device to shock, and then it's about
Right. Yeah, I have seen those kind of results too, but we are trying to actually help the lifestyle issues a little. Managing the lifestyle. Lifestyle is not the right word, but daily life, a little better. So.
Is it possible to have a generative AI model for this? Based on some success stories.
So.
And that's where I said that you have data, but you also require a model. A numerical or a something like a partial differential equation generated from your model, so that
Yeah.
we can fit all of this
Right.
and get that. That would be really helpful.
Yeah. There are models available in the literature. Okay. Physiologically based models are available. Some of the work that the data augmentation work we did is generative AI. Okay. But it's a blind generative AI, blind model basically.
One of the things that we need is to introduce uncertainty into modeling.
Yeah. Yeah.
And if you have uncertainty into modeling and quantify it statistically,
Right.
then we will not get exact, but we will get a range.
Right. No. The thing is, I don't believe that we need to precisely match the characteristics to actually do well.
Yeah.
In fact, if you do not precisely match, you might do a little better because the training will be a little bit more broadly based.
So the reason why I asked is for my health monitoring,
Yeah.
which is also a waveform.
Right.
We deal with time signals.
Of course.
We have generated the partial differential equation,
Right.
assuming certain form. Okay, it will be second order in time, second order in space,
Yes.
and added a mixed derivative also based on this. And certain constants were there, and that becomes my generative model for any kind of defects that I find in structure.
Right.
But here I find defect in brain.
Brain. Yeah. Yeah. Again, I think I haven't done it, but it's something that's worth looking at for sure.
So any more questions?
Any more questions?
So if you don't have, so let's thank Professor Matthews for a wonderful enlightening talk, bringing science, medicine, engineering, AI into one space. So on behalf of Axis Bank, I would like to give him a very small memento.
Thank you.
So I invite all of you to join lunch. We have arranged lunch for all of you. And thank you all for coming. Thank you.